I was putting the last bit of waffle batter into our waffle iron, and I knew it wouldn't fill the entire thing, but I was a bit surprised at the shape that came out. I'm sure I've done this before, but never realized that the shape that comes out, this square, is actually a circle. Well, it might be clear to some of you how this square is a circle. I'm using the word circle in a different way than referring to a particular geometric figure. There are actually lots of shapes that can be defined as circles for given situations. This is a circle to a king on a chessboard. This is a circle to lifeguards on a beach. And this would be a circle to taxicab drivers. The word circle in mathematics refers to a shape and an idea. The shape we're all familiar with. The idea comes from the definition of a circle. It is the set of points that are the same distance from a given center. Seems straightforward, and at first seems like the circle shape should always be the result, no matter how you apply the definition. After all, you can use a compass, which holds the two ends apart at the same distance, and generate these points on a piece of paper. There is no way you're going to make a square spinning a compass. Well, actually, if you watch to the end of the video, you can see what I came up with to do just that. But things get interesting because of this one word in the definition: distance. The distance formula taught in school, called the Euclidean distance formula, is not the only useful distance formula. There are other distance formulas which mathematicians call metrics. A circle to a pancake is not a circle to a waffle. So let's explore some situations to understand why there are so many different circles that don't look like circles. If you put a scoop of batter on a flat pan, it will spread it into an approximate circle. Put the same batter in a waffle maker, starting in a circular shape, and if it isn't enough batter to reach the edge, it doesn't come out in a circular shape. Why? Because as the batter spreads, it's forced to only move along the grid lines. These edges are the same distance away from the center because the batter can't take a direct path outward, like the batter on a pan. So for the batter to get to here, it has to travel the same number of grid segments to get to here, or these other spots. A circular shape doesn't make sense in this context, but this square shape, rotated 45 degrees from the squares on the grid, does make sense to be the circle to the waffle batter. Now, why didn't I call it a diamond? Because there is no diamond shape in math. What most people call diamonds are just squares, or sometimes a non-square rhombus, just oriented in a certain way. Rotated squares emerge as circles whenever we are in situations where travel is limited to grid lines. One common situation is driving in a city where streets are set up in a grid. When driving, we're forced to go along the roads, so the points on where we could end up after going 4 blocks fall into this square. The distance formula for these situations is this, and is called the taxicab metric because driving to any point on this figure will cost the same taxi fare. Okay, if you try to drive to one of these points off the street, it might cost you a lot more, because you might need to drive through the front window of a building to get there. Distances are different in the game of chess. We will look at 2 examples, the king and the rook. For a king, all squares touching the king square are 1 move away, or 1 block away. Then each square touching those squares are 2 moves away, etc. To a king, squares oriented with the grid are circles. The shortest paths for a king are combinations of diagonal and grid line moves. What determines the number of moves away a certain space is, for a king, is the largest of either the x or y distances to the new space. So the distance formula for the king is this formula, and is also known as the Chebyshev distance. Now, it might be silly to create a formula for a king in chess if that's the only place it could be used. Don't worry, it is not. Overhead cranes that can move horizontally and vertically use this metric for items that are the same distance away. With both motors on, the crane moves diagonal, which takes the same amount of time as moving the crane to any point on a square oriented with the beams of the crane. Another place where this definition of distance is used, and actually all of the distance formulas that we've discussed so far, is in computer graphics, where programmers use different distances to create filters and effects and edits on images. Because digital images are created by pixels, which are small squares in a grid, taxicab or king move distances are both quite natural. What is a circle to a rook? Well, it depends. If we're going by blocks, then we're back to the taxicab geometry. But if we go by moves, then circles are cross-shaped, or something weird. These are all cells 1 move away for a rook. All other cells are 2 moves away. If no other pieces are on the board, even on an infinite chessboard, the farthest a point can be from a rook is only 2 moves, so 2 is the maximum distance. So to a rook, there are only 2 circles with positive radii. This one and this one. Measuring distance in time often leads to weird-shaped circles. For example, since a lifeguard can run faster on the beach than swim in the water, then looking at all of the places a lifeguard could be in the same amount of time gives this kind of shape. It is a portion of our traditional circular shape on the beach, but a curve that's not quite a portion of a circular figure in the water. One takeaway from this is to not swim too far out into the ocean because it seems like you're not very far from the lifeguard by line of sight, but it can still take the lifeguard quite some time to get to you out there. Using time to deliver a package creates some different circles on the US map. Here's an image that shows where the US Postal Service delivers a letter from New York for a different number of days. Here's another one by the company FedEx and packages delivered from Chicago. It is interesting to see the islands where it takes more time to get to. So what we are learning is that the shape we call a circle for different contexts and different distance measures might not look like a Euclidean circle. We could measure distance by intensity. Suppose someone is talking in the hall. All the places where people would hear the words at the same volume depends on the walls, corners, and how much objects dampen the sound. So even if you're close by Euclidean distance, but behind a door, you could be considered further away compared to someone down the hall without any obstructions, because they could hear better than you. Well, if we are in a situation where circles are not traditional circles, then the math that depends on circles also changes. Consider the trigonometric functions that are closely tied to a unit circle. Well, for the king on the chessboard with his quote-unquote square circles, he doesn't care about sine and cosine, but squine and cosquine. And no, I didn't make up those words. They're variations adapted to the Chebyshev metric. You can learn more about squine and cosquine and tanquint in this video by James Tanton. Even if you don't ever use these, understanding them will help you better understand the meaning of the trig functions that are widely used. Do you know of other situations where a circle isn't a circle? Share them in the comments. We didn't have a chance in this video to talk about how properties of the surface you are using can also change a circle, or how to draw a circle. If you change the surface properties, then what you think is a circle might not actually be a circle. I sat down and did the math to develop this device that actually allows a regular compass to draw a square. Let me know in the comments if you'd like to see a video on the math behind this square compass device. So next time you see a square like this and you're tempted to call it a diamond, call it a circle and you'll be more mathematically correct. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.